Hello and welcome to my channel, Quantum Pinguino. Today I'll be discussing causality in quantum field theory as argued in the textbook Introduction to Quantum Field Theory by Peskin and Schroeder. I'll first describe why relativistic and non-relativistic quantum mechanics alone are not sufficient and violate causality, while a quantum field theory, such as the one described for spin zero particles by the Klein-Gordon equation, does preserve causality. First, let's start with the definition of the amplitude of a particle propagating from state x0 to x using non-relativistic quantum mechanics. Here, we use the time evolution operator in the inner product between these two states to represent the propagation. Then, we substitute the expression for non-relativistic energy into the Hamiltonian. Next, we use the completeness relation to algebraically manipulate our integral. The completeness relation is essentially 1, but this allows us to write an outer product between two momentum eigenstates. We can use this to rearrange the contents of our integral such that we then have inner products between momentum and position eigenstates. This is good for us because then we can substitute the expressions of the inner product between position and momentum eigenstates into our integrand. Now we want to take our new expression and convert it into polar coordinates. I use these boxes to help identify the different parts of the polar space we're working in. In blue we have momentum, in red we have over cosine theta, and in orange we have over d phi. We're going to take each of these three integrals separately. We can first do the integral with respect to d phi trivially to just get a factor of 2 pi as there's no explicit phi dependence, but then we do have to take care when we integrate with respect to d cosine theta, as one of our exponentials has a factor of ip delta x cosine theta in the exponent. Taking this new expression, we know that it's actually a difference between two exponentials that look very similar. In fact, we can exploit the symmetry between them by changing the coordinates of the rightmost integral to p prime, where p prime is equal to negative p. After performing this transformation, we note that this new integral in terms of p prime is the exact same as the leftmost integral in the topmost equation, except for the fact that it has orthogonal boundaries. We can then exploit this to add these two integrals together into a single integral and realize that the expression now looks eerily like a Gaussian. It doesn't just look like a Gaussian, it's actually the derivative of a Gaussian. So we can undo this derivative by adding the derivative factor in front of the integral so that our integrand is strictly Gaussian. This allows us to then exploit the integrand being strictly Gaussian by finding an analytical form for the integral. Now the rest is super straightforward. We just have to take care of this derivative that brings down a factor of im over 2t from the exponential, do some simplification, and arrive at the answer provided on page 14 of Peskin and Schroeder. What this expression is telling us physically is that we can choose an arbitrarily small time and an arbitrarily large difference between the two states we want to propagate between, x0 and x, and still have a non-zero amplitude for the probability of this propagation occurring. This in and of itself is a violation of the principle of causality. Now, instead of giving up and crying, we'll instead try to use relativistic quantum mechanics to see if we can preserve causality by using a different expression for the energy and momentum. I'm skipping a lot of steps since the workflow is essentially the same as what we did for the non-relativistic case, and we get to the point where after we convert to polar coordinates and do the d phi and d theta integrals, we have these two expressions in our integrand. However, instead of doing the transformation of p prime equals negative p to concatenate the two integrals into one, we instead simplify the integrand directly by writing the expression as a sum of two signs. For some godforsaken and unholy reason, two mathematicians in the 1980s came up with a closed-form analytical expression for this integral in terms of the modified Bessel function of the second kind. This expression is given on the bottom left, and we apply it to our integral to derive our final result. After some simplification, we arrive at our final result. Again, this expression violates causality because we can choose an arbitrarily small time and arbitrarily large delta x such that the amplitude of propagation between states x0 and x is non-vanishing. I included this image from Wolfram Math World showing the behavior of the modified Bessel function of the second kind, which shows that it does become exponentially smaller but never completely vanishes. As a result, relativistic quantum mechanics does violate causality. So it might seem like we're cooked. We got two theoretical frameworks that don't preserve causality. However, This is the whole argument Peskin and Schroeder present for needing a theoretical framework such as quantum field theory that does preserve causality. The argument that we will use to show that QFT does not violate causality is using the Klein-Gordon equation. Chapter 2 of Peskin and Schroeder goes into more depth about this, specifically sections 2.2 and 2.3. I'm just going to use the results from those sections to make the arguments of causality presented in 2.4 of the same chapter. We first start by defining the Lagrangian for a single field, and from this Lagrangian also taking the equations of motion. I write the Lagrangian equation of motions in two forms, one with using standard derivatives and the other using the Ford derivative. The argument in section 2.3 of Peskin and Schroeder is to make an analog of the Klein-Gordon equation to a simple harmonic oscillator. This allows us to define a few properties of the Klein-Gordon equation. First is that the field can be represented as an integral over the raising and lowering operators in momentum space. Second is that the frequency of the harmonic oscillator used as the analog to the Klein-Gordon equation is simply the relativistic relationship between energy, momentum, and mass. And finally, an expression for the commutation relationship between the raising and lowering operators in momentum space. In the Heisenberg picture, we can express the amplitude of propagation from y to x in terms of the Whiteman function given at the top. First, let's assume a purely time-like separation between x and y. We first change into spherical coordinates, as we have before, and we evaluate the two integrals in terms of cosine theta and d phi. Our integrand has no explicit dependence on these, so these can be trivially evaluated. We follow this with a change in variables from momentum to energy using the relativistic energy-momentum-mass relationship. This allows us to evaluate our integral analytically using the modified Bessel function of the first kind. In addition, we can perform a first-order expansion of the Bessel function given by Abramowitz and Stegen 9.7.2, allowing us to recover the final result given in Peskin and Schroeder 2.51, which is actually that this amplitude does not vanish for all time. This is a bit strange as our previous arguments were that vanishing amplitudes implied no violation of causality, and here we don't have a vanishing amplitude, which would imply a violation of causality in QFT. The argument presented by Peskin and Schroeder is slightly nuanced, and I will elaborate a bit more upon it once I also derive the amplitude for the space-like separation in the Whiteman function. So for the space-like case of the Whiteman function, we instead assume that the separation between x and y is purely spatial and there's no temporal separation. We can evaluate in terms of polar coordinates, and we get this nasty expression where we evaluate already the d phi integral, but still need to evaluate the d theta and momentum integral. The integral with respect to theta is a lot easier than it looks. It's just the derivative of the exponential with respect to theta, which we can easily undo. This leaves us again with a sum of two exponentials. However, we can easily relate them by performing the earlier transformation we did of p prime equals negative p. This allows the integrands to look exactly the same, but have orthogonal boundaries of integration, allowing us to concatenate them into a single integral. We can evaluate this integral using complex analysis by knowing that the denominator has two singularities at p equals plus or minus im. We can first perform the transformation rho equals ip, and push our contour to wrap around the upper branch cut singularity. This allows us to redefine our integral in real space as given below. Then it is an easy matter of applying the definition of the modified Bessel function of the second kind to derive an analytical expression for our integral. Once again, we perform a first-order expansion on the Bessel function similarly to how we did in the time-like case to find that the space-like amplitude of the propagation from y to x is non-vanishing. Now, this is where the nuance of Peskin and Schroeder's argument comes in, and it had me a bit confused at first. What they're arguing is that what we're really seeing with this non-vanishing amplitude is the correlation between y and x. The correlation between y and x does not necessarily have to be zero, because, for example, if you went arbitrarily far enough back in time, it's very possible that y and x could have had overlapping light cones. Another way of thinking about this is, let's say you had a friend that went to y and you went to x, and both made a measurement at these points. Then you took some time to meet up with each other again that did not violate causality and shared your results. Your results themselves could be correlated. However, each of you making that measurement did not affect each other's measurement. This idea of simultaneous measurements not affecting the results can be checked by instead looking at the commutator between phi x and phi y. So Peskin and Schroeder's argument is that the correlation between y and x doesn't have to be 0, but the commutation between them has to be, so that simultaneous measurements do not affect each other and violate causality. And we can demonstrate this now. So let's write the commutator out explicitly. We assume that the fields x and y have momenta p and q respectively, and then only write the commutator brackets around the operator portions of our expressions. Here I'm going to argue a few things about this commutator. First is that we are going to have to necessitate that p equals q, as otherwise everything will vanish, since we're going to be multiplying operators corresponding to different momentum spaces. Next, any term that has a double raising or double lowering operator is going to vanish because of the AB minus BA symmetry from the definition of the commutator. This means that the only terms we're going to have left are the cross terms between a raising and a lowering operator, which there are exactly 2 of. We can evaluate the non-zero cross terms in our commutator using the commutation relationship between the raising and lowering operators derived by Peskin and Schroeder in section 2.3. This allows us to find a closed form for the commutation relationship between x and y, which we can then express in terms of the Whiteman functions, one being a function of x minus y and the other being a function of y minus x. And although it seems like these two terms won't cancel out, we have one more trick up our sleeve, and that's if the difference between x minus y is space-like, then we can find a continuous Lorentz transformation that takes us from x minus y to y minus x. This allows us to rewrite the second Whiteman function as d of x minus y so that it cancels out with the first, and thus we get that the commutation relationship between x and y is 0, thus preserving causality. Thus, we finally made it. We've shown that QFT preserves causality, and even though the propagation amplitude between x and y may be non-zero, this is okay. This just represents the correlation between these 2 points and not whether simultaneous measurements can be propagated faster than within their light cone. I hope you all enjoyed. I'll include a link to one of the discussions I had that made more sense of this Peskin and Schroeder argument about why causality is preserved if the propagation amplitude is non-zero. And yeah, I mean, this is my first dive into quantum field theory, so if you guys have any comments, maybe I said something wrong, please let me know. Thanks for watching.